Good morning, everyone. Thank you for taking the time to come and attend my dissertation defense for people who are joining both online and in person. I hope your plate is full because we are going to be talking about food in the first half of the presentation. And without further ado, let me jump into the topic. I'm here to defend my dissertation title, Explainable Process Recommendation through Multi-Contextual Grounding of Dynamic Multimodal Process Knowledge Graphs. My committee consists of Dr. Amit Sheikh, my advisor, who is an NCR chair, founder of AISC, and professor at Computer Science and Engineering Department. Dr. Biplav Srivastava, who's my examination chair, professor at Computer Science and Engineering Department, and Dr. Vignesh Narayanan, assistant professor at Computer Science and Engineering Department, Dr. Suparna Bhattacharya, who's a vice presidential fellow at Hewlett Packard Enterprise, and Dr. Swati Padi, postdoctoral researcher at Ohio State University. So let's start with a motivating question. Can I eat this food or not? So this was a question my father started asking when he was diagnosed with diabetes. He used to spend hours meticulously researching about food to plan his meal and his diet management. So years later, when I was working in AI and diet management, I realized that this is a question that's asked by millions of people all around the world to manage their chronic conditions or for dietary restrictions. So it would be helpful for these people if given a food image or a recipe text like that, such an explanation can be made. So something which says whether this food is suitable or not, and also explains why it is suitable and why it is not suitable. So in order to do that, we need a recommender that can look into the ingredients, cooking methods, and interactions and draw individual inferences on whether they are suitable or not. So to do that, the recommender will need access to the domain information and the disease contextual information. Along with that, it will also need a little bit of past or observed data to meaningfully assign weights to each of these individual inferences and make a collective decision on why it is supposed to be recommended or not. So the process of collective decision making over individual inferences is called compositional reasoning. Now let's look into a completely different domain. Which AI pipeline is best suited for a given task and a data set? So this is a question that's asked by us researchers, AI researchers specifically, because it has become increasingly costly to train the models because of the size and the pace at which they are growing. So let's say we have a question like this. Pipelines executed for visual question and answering using Flickr 30K dataset with an accuracy above 75%. So it would be helpful for us if such a recommendation can be made saying that this pipeline is relevant, this pipeline is relevant, and why these two pipelines are relevant. Now, the explanations in both the domains are essential because the first one is self-explanatory, and in the second one, because of the time and compute resources, we need to let the users make an informed decision as whether they would like to first go ahead and execute this pipeline or not. Now, in order to do that, again, we need a recommender here that will look into individual pipeline components and rank their relevancy as how relevant they are to a given query. So in order to do that, the recommender will need access to metadata of AI pipelines executed in the past so that those pipelines can be taken and ranked accordingly. And to rank them, to rank the relevancy, we will also need access to domain knowledge. So for example, here the task is visual question and answering. When we look at the first pipeline, the task is very evident, visual question and answering. The pipeline 2 is actually a visual and a question and answering task, though it's not very evident from the task name itself. And for the next pipeline, which is just a question and answering task and does not have a visual component associated with it. So given that, to summarize the needs, these are the following need to execute the problem statement that we have just proposed. First of all, if we notice, both of these require structured data, meaning that both are procedural data which requires step-by-step execution. So we do need structured process data. And the second one is the multi-contextual knowledge. We need domain expert knowledge or in both the domains to draw meaningful insights. And the next one is methods for process recommendation. So item recommendations are easy, where only a given item is analyzed. But for process, multiple items in a given for a given data point needs to be analyzed. And the fourth one, explanations for the recommendation. Given the high stake domain in both the cases, we need explanations explanations to be provided to the users so that they can make an informed decision making. To execute this, when I tried to execute this, I was faced with 4 challenges as we see here. The first one is the unstructured data, meaning that both in case of recipes and in case of AI pipelines, the data is in unstructured format and not structured format. So that is the problem. Both are in natural language text. For example, every published paper is an AI pipeline. The second one is the lack of domain knowledge. There is no collective domain knowledge available for both of these domains. And the third one is explainable process recommendation. So we need a method to do process recommendation, which is also explainable. And the fourth challenge is, do the users accept these explanations? When we looked into the existing works for process recommendation, the algorithms mainly focus on these 3 aspects, meaning there are algorithms to identify similar words in 2 processes to rank their similarity. And the second one is the behavioral similarity, which takes into account the order or stages of execution of a process. And the graph-based similarity that uses classical graph similarity algorithms such as graph edit distance or graph isomorphism. So looking into the existing works, we see that the challenges still remain, mainly because the existing works assume availability of structured data, but that's not always the case. And they neither focus into the explainability or use of domain knowledge for more meaningful insights into the inferencing. So now mapping these challenges to the research questions, how can we extract?
I would like you to explain what is the process. And number 2, if anyone has a copy of the slide, if they can just name the committee, please. Just
Okay.
the slide that we're using.
Okay. Okay. Okay.
So the first thing, explain what is a process.
Okay.
What do you mean by a process? And the second is we don't like to stop it now. So
I have the explanation for the process in the upcoming slides.
Can please do that first.
Okay. Okay.
If it's not a problem.
Actually, let me go over with the flow because it's at the end. And so the process looks like something as we see here, which includes a step-by-step execution of step-by-step executions of small actions to arrive at the final output. So for example, in case of recipes, we bring the ingredients and cooking methods together in one step and the second set of ingredients and cooking methods in the next step. And we perform these sequentially in a temporal order to arrive at the final recipe. Similarly, for AI pipelines, it also consists of several stages. We start with data selection, data pre-processing, model selection, training, hyperparameter tuning, and finally the model goes for the deployment. So these sequential steps, which we execute in order, constitutes a process. So for example, here, this is an example. This is a first half of a process for potato fries. So let me quickly go into the research questions and then come to each of the explanations because there are a lot of new words in the thesis. So given a natural language text, first research question is, given an unstructured data, how are we going to extract the structured data using limited ground truth or using domain knowledge? Because generating the structured data would be a challenge if we are trying to create a large scale version of this data for just extracting the entities out of it. So we need to somehow leverage the limited ground truth that is available or use the domain knowledge to get the structured data out of it. Now, the second question is, so given that we have extracted the entities, the word potato or the input of potato does not mean much to the model. So how are we going to elevate this low-level data to the high-level knowledge? For example, potato is considered a healthy carbohydrate because it satisfies the ratio of 10:1 for carb to fiber. And for that reason, it can be recommended for diabetes. And and it also has a glycemic index, for which reason it is supposed to be had with caution. So such multi-contextual knowledge is essential, and we need to elevate the low-level data to high-level knowledge. And the next research challenge is, so given that we have extracted the processes and extracted the entities and grounded them in knowledge, how are we going to put together to make explainable process recommendation? And the next challenge is, do the users accept the explanation? Do they find the explanations clear, relevant, trustworthy, and are they satisfied with the format that we are giving the explanations as well? And that brings to my thesis statement, neurosymbolic approach for explainable process recommendation through multi-contextual grounding of dynamic multimodal process knowledge graph to enable reasoning traceability, enhancing the recommendation accuracy and trustworthiness. Now, there is a lot of new terms here. Let me quickly go over them, what that means for both the domains. For example, the process graph in both the domains looks as follows, where the ingredients interact with the actions in each step, and at the end, a final output recipe will be obtained. The equivalent of ingredients in AI pipelines is the data set, metric, and models. And the equivalent of cooking actions is the actions that we perform, such as data set selection, data set preprocessing, model selection, and answer. And when we take this process graph and ground it with knowledge, it becomes cooking process knowledge graph or AI pipeline process knowledge graph. So here we have contextual information for ingredients such as butter and stew, and also what happens if a particular ingredient interacts with a cooking method, what are the effects of it. And similarly, the AI pipeline process knowledge graph is also grounded with knowledge. Here, since AI pipeline is not a natural science domain like food, which has been researched for a very long period of time, the amount of contextual knowledge there or what to look for is already given and it's generally rich. But in case of AI pipelines, which is an upcoming domain and also a man-made domain, the type of semantic properties to ground them are not so high. But at the same time, they do have rich description explaining what each of them are, so which can be leveraged to construct the semantic properties. The multimodal data for recipe process graph looks as follows, where we have ingredient images and food images. And the multimodal data for AI pipeline looks as follows. It consists of documents that explains the details of AI pipeline executions, the images that is present in the document, and by default, we have the text and numerical data. We also create embeddings for the node text because embeddings are a good approximation of variable length information. So the descriptions are of variable length. So constructing an embedding for that will help us compare the embeddings or find similar entities and so on. And so given that,
what do you mean by S1 and S2 here?
So these are intermediate states. Those are formed that's just used for the representation at this point. And the reason for using that is, let's say, to promote further work, and I'm not heavily using it in my work. So for example, when we perform cooking actions, step 1, step 2, and step 3 will yield an intermediate product. When we perform step 4, that intermediate product will keep changing. So if we want to interfere somewhere in between and change the cooking method or ingredients, so we can study those intermediate states. And that's the reason why we have those intermediate states. So the rest of the presentation is outlined as follows. We are going to explore the 4 research questions in these 2 domains to do explainable process recommendation, recipes being a process and AI pipeline being a process. Let's start with the recipe domain, explainable recipe recommendation in the context of diabetes. Why do we need food recommendation? So diet plays a major role in management of chronic diseases. But to analyze a meal is very tricky because we have ingredients, cooking methods, nutrition, and calorie contents to put together. And as we mentioned before, the guidelines for the contextual knowledge for the dietary restrictions or chronic conditions are also not available in one place. They are scattered across multiple places. So analyzing these multiple components, bringing in information from multiple sources on a day-to-day basis is an tedious task. The existing works there are a lot of existing works on meal recommendation, but they do not focus on disease-specific recommendation by adhering to strict medical guidelines, and neither do they factor in the cooking methods in their recommendation process. So this is what we are planning to do here. Just to recap whatever we saw in our initial slide, we're going to make explainable recommendation and say why a food is suitable or not suitable. That brings us to the first research question, extracting entities out of the natural language text to construct the process graph. First, extracting ingredients. Generally, when we look at recipes, the list of ingredients is given in the respective blog post, but the order of usage of those ingredients is generally not given. So to do that, we took the recipe text, extracted or separated them into sentences, gave it to a spacey noun parser to get all the noun terms out of it. But in recipes, in addition to ingredients, we also have other noun terms, such as the tools that are used for the cooking process. So the list of ingredients that were given to us in the beginning of the recipe, we used that to do the IOU computation on top of it to get the corresponding ingredients involved in each of these sentences. And at this point, we assume that each sentence corresponds to each step. And we also went for IOU computation and not string-based match because a recipe can be mentioned as ingredient can be mentioned as Philadelphia cream cheese in the list. And in the recipe text, it's generally mentioned as cream cheese. So in order to account for the variations, we went for IOU computation. But extracting cooking actions were not as straightforward as extracting ingredients because it was already given. First, there was no availability of ground truth data. So we created our own ground truth by taking instructions from 1,000 recipes, which constituted 10,000 cooking instructions. But there were so many statistical irregularities in the cooking instruction data set. So 10,000 was not sufficient to manage for those statistical irregularities. So some examples of statistical irregularities are as follows. So both the sentences are conveying the same but using different words. And each cooking instruction are of extreme variable lengths. Some are 3 words long and some are 20 or 30 words long, which is extremely lengthy. And also, given this text, the number of words that account for cooking methods is very less compared to the other information that is present. And also irregular distribution of cooking methods itself. The word boil is present way more compared to word broil in the data set. So this prevented existing off-the-shelf models like Electron, ExcelNet to mine the patterns. So in order to account for those statistical irregularities and also manage with the limited ground truth data that we have, we came up with an approach called approach that accounts for the statistical irregularities. It is based on polynomial aggregation based approximation. This will help the models diminish the statistical irregularities by mapping the data distribution of the train and test data to be the same. So the CookGen model performed really well, achieving an accuracy of about 99% compared to the next highest model, which is Electra, which was about 91%. On the contrary, the parameter size of Electra is 300K and the parameter size of CookGen is just about 20K, which helps us easily deploying these models into mobile and edge devices. Next, so given we extracted these two entities, we need to look into their interactions. So we have an instruction, we have an ingredient, we have the cooking actions. We might think that the problem is solved, but there are multiple cooking actions involved in a given instruction itself. So the word mix here is performed on butter and steak seasoning, and the marination is performed on steak. So how to extract these interactions and the dependencies? So this is where large language models came to the rescue, did not need any training, but required heavy knowledge guided prompting. So we told that this is the ingredient, this is the cooking method. So give your output only based on what is given in the list and don't pick up something on your own. So the models strictly followed the instruction that was given, and we were able to get the interactions. We had the database of images which we mapped to the respective entities that we have here or crawled using Bing API crawler. The model achieved about 97% accuracy. The problem is because people started using noun terms as verbs. For example, butter the sheet, oil the pan. So those are technically noun terms, but it became verbs. So only in those cases, the model suffered a bit. So given a text, we saw how to extract the ingredients and cooking methods. What happens when a recipe image is given? Generally, what approach is followed is cross-model retrieval learning. So given an image, corresponding text is obtained and an embedding is generated for both, projected onto a learned embedding space, and an objective function is used to bring these two embeddings closer in the latent space, which is called cross-model retrieval learning. And on top of that, some sort of clustering is applied to bring similar recipes closer in the latent space. For example, fries are grouped together, salads are grouped together there. This is a very good approach. Let's say we have a cluster of bagels and burger. Which cluster would this image go to? It has bagel, but all the ingredients that is supposed to be in a burger. The calorie difference for burger bun and bagel bun is about 100. So we don't want to put it in the wrong cluster as well. So instead of class names, this is why it is happening. When we are grouping based on class names, that's why the problem is. So can we group based on something else? So that is where we came up with recipe similarity determinant, and we followed an approach called knowledge infused learning. I'll tell you in a little bit what that is about. So we came up with the recipe similarity determinant under the intuition that similar recipes have similar titles, similar set of ingredients, and similar set of cooking methods. So this one accounts for counting those similarities and giving up a semantic similarity score, which is infused into the model training process to arrange the recipes as we see here. They are not clustered, but they are arranged just based on their similarity. Now, this KI Cook, the knowledge infused cooking model, we evaluated this on ingredient retrieval process, meaning that given these query images, retrieve the corresponding text embedding, get the ingredients out of it, and check how many of those ingredients overlap. We observed something very interesting when we did this, because we have a base model that is trained without knowledge, and we have a model that's trained with knowledge. So you can see that the accuracy here, we have three types of accuracy, where the accuracy of the knowledge infused model is same as the base model, higher than the base model, and lower than the base model. In all the three scenarios, the knowledge infused model picked more relevant recipe compared to the base model. For example, when we take an example of fried eggplant, the base model retrieved Dilly cheese muffins as the relevant text, recipe text, whereas KI Cook model identified it as low carb eggplant parmesan. Similarly, for cheddar cheese chive biscuits, KI Cook model guessed that it is peppery cheese and chive biscuits, whereas the base model guessed it as chocolate chip cookies. And the same goes for the last one as well. So this shows the importance of knowledge in guiding the model training process as well. So where we use the neural component heavily and a little bit of symbolic component in these entity extractions. That brings to the research question 2. So how are we going to elevate the low-level data to high-level knowledge? First, we looked into the list of knowledge sources we would require to analyze a recipe in the context of diabetes and found the appropriate sources which provides this knowledge. First, starting with diabetes medical guidelines, Mayo Clinic says that these are the ingredients or recipes which are supposed to be recommended and which is supposed to be avoided. And on the other hand, we have a large-scale ingredient database from US FDA. But how are we going to map this to that one? What constitutes a healthy carbohydrate? What constitutes a good fat? So this again required meticulous research looking into several sources and published papers to say what constitutes a whole grain, what constitutes a fiber-rich, non-fat, low-fat, so that the nutrition content of the US FDA can get that and appropriate maps can be made. And when we made the mapping, it resulted in a graph like that, where we have an ingredient from US FDA, pork ground raw, which is mapped to several food groups from diabetes, good fat, animal protein, low sodium, and etc. And we also have the eventual mapping of whether it is supposed to be recommended, avoided, or had with caution. So the graph might look simple here, but each of the nodes and relationships hold rich information. So the relationship belongs to here hold the following properties, which says, why did we map pork to high cholesterol? And where did I get this information from? Which source told me that the allowed level of high cholesterol is 200 milligrams per day? So we have the source information as well, so that we can make explainable and traceable recommendation. Traceable recommendation meaning the explanations can be traced back to a trusted source. And the next type of knowledge we have is cooking taxonomy, since we were planning to look into the effects of cooking methods as well. So the cooking taxonomy is obtained from Wikidata and DVpedia. It's classified into three major categories: heat-based, mechanical-based, and chemical-based, where the heat-based cooking method is further divided into dry heat, liquid-based, and fat-based cooking method. And we have the cooking methods for each of them. And we have a description of what each of the cooking methods mean as well, which can be used for further analysis. So bringing the ingredients and cooking methods together, a constructed carcinogen causal knowledge graph. Here, we looked into several literatures and we found that when an ingredient undergoes certain set of cooking methods, it results in the formation of carcinogenic compounds. Carcinogenic compounds meaning cancer-causing compounds. Though they are produced in traces, frequent consumption of those could be detrimental for health. We focused on 3 heterocyclic amines, polyaromatic hydrocarbons, and also advanced glycation end products. The reason for the formation of the carcinogen is stored in the relationship and or in the node properties as we see here. It also has a list of cooking methods and list of ingredients, the combination which when undergone, so produces the carcinogens that we have there. The sources are Healthline and published papers. Next is a smoke point knowledge. When fats and oils are heated beyond their smoke point, they produce free radicals, which are toxic compounds. So here we have all the oils and fats from US FDA mapped to the categories such as high smoke point, low smoke point, medium, low, and etc. So I found an example here which was interesting, which was a new information to me as well. So I was also under the impression higher the smoking point can be used for deep frying and high temperature cooking. We have walnut oil here, which has 430 degree Fahrenheit, which is 430 degree Fahrenheit. Sorry, has a smoking point of 430 degree Fahrenheit. However, it cannot be cooked to that temperature because it will result in bitter flavors. So it should actually be used with no to low heat to make sure that it doesn't result in something very bad when put into the recipes. The next and most important one is the glycemic index knowledge graph. Glycemic index measures how quickly the carbohydrate containing foods rise the blood glucose sugar levels, which means that high glycemic index foods are bad and should be supposed to be had in moderation or be cautious when we are having it. And the low glycemic index food are good because it slowly elevates your glucose levels. For the GI, the Sydney University had their own database with 4,000 ingredients, and the ingredient names are the brand names themselves. So in order to retain the originality and not to mess it up, so we use the large language models to identify the core ingredient in USFDA database for each item and also the core ingredient in glycemic index. So for example, though the names do not exactly match between the US FDA and also the glycemic index ingredients, both are talking about maple syrup. So that's how we created this mapping. I created using cosine similarity, which is also stored. Anything above 0.8, we create a mapping there. So this is a graph overview. When constructed in label property graph format, we have 17,000 ingredients, 677,000 relationships. When we put it as RDF format, it has about 1.2 million triples, just to give an idea. So we have extracted the ingredients, we have gathered several knowledge sources, and we have elevated the low-level data to high-level knowledge. How can we represent all of them together? So that's why I came up with a representation called Dynamic Multimodal Process Knowledge Graph for recipes. It consists of recipes in their structured format, which has the ingredients and cooking methods extracted, the raw format of the recipe, and also the recipe images and recipe ingredients to facilitate neurosymbolic-based queries as well. And each of these entities is grounded in knowledge, which can be brought together using any model that we would like to make inferencing or do any kind of additional processing. So while we are going to use this for our explainable process recommendation, let's also quickly look into what other things the dynamic multimodal process knowledge graph can do. So let's say a user has a query, make fried steak tacos suitable for diabetes and vegetarians. So with the help of the representation that we just proposed, we can infer that steak is an animal product incompatible for vegetarian. Sour cream has high fat, not suitable for diabetes, and deep frying introduces trans fat. And the dynamic process knowledge graph can also help us find modifications as we see here. Replace steak with cauliflower, replace sour cream with yogurt, replace deep frying with air frying. So we did construct a large-scale multimodal ingredient substitution knowledge graph with 80,000 ingredient substitution pairs that has health labels such as whether an ingredient is vegan, vegetarian, lactose-free, gluten-free, and nut-free, which can help us with the first two modifications. And the cooking taxonomy here can say that replace deep frying with air frying, while boiling can be a much better and a healthier alternative, but it's a liquid-based cooking method, not a fat-based method. So we have to find an alternative accordingly. And it can also enable neurosymbolic queries as we see here. So user can give an image and ask, give me recipes with this ingredient, or give an image and ask, is this recipe suitable for diabetes or not? So that brings us to the major research question, which is research question 3. And we have a data set, in order to first construct a method and validate, we need a data set which has list of recipes suitable for diabetes and list of recipes not suitable for diabetes. The recipes suitable for diabetes were obtained from sources we have here, where they have recipe cookbook sort of thing to recommend recipes for diabetic patients. And using the keywords given by Mayo Clinic for the avoid categories, we use those keywords to construct to identify recipes from recipe 1M dataset that will for sure be not okay for diabetes patients. So the first step in our recommendation is we have the ingredient from our recipe, let's say sesame oil, but that's not the exact name that's present in US FDA. So it's usually present as oil, sesame, salad, or cooking. So we need a mapping function that maps the recipe ingredients to the database ingredients that we have here. So we came up with a combination of embedding-based similarity and set similarity of the ingredient tokens we have, which is just a Jakarta similarity. So putting them together we identify what is the appropriate ingredient match to the list of ingredients that is present in our database. So this talks about the neural component of the neurosymbolic recommendation that we were talking about, where we were using embeddings to find appropriate mappings. And once we do this for each of the ingredients in the recipe, we will have something as follows. So for all the ingredients in US FDA, we have created appropriate reasoning as why they are suitable or not suitable. And through the process graph that we have generated, we can study the interactions and also find those interactions in our knowledge graph to see if they produce any harmful effects or whether they should be recommended or not. So once we made these individual inferences, there are a lot of reasons to recommend, avoid, or have this food with caution. So how are we going to put them together to say whether it is supposed to be recommended or not? So for this, I introduced a method called knowledge graph-based Bayesian inferencing. Initially, the question we had is, given this set of ingredients and set of cooking methods, what is the probability the recipe is suitable for diabetes or not? So here the question now slightly changes. Given these list of knowledge paths, what is the probability the recipe is suitable or not suitable for diabetes? And this is a simple Bayesian equation. So given these knowledge paths, we are going to evaluate what is the probability that the recipe is suitable or not. So I'll go over the details of this Bayesian inferencing in the supplementary section, but in the interest of time, let me quickly go over and show how the results look like. Oh, okay. We compared it against several baselines. Obviously, the KG-based Bayesian performed really well. The overall findings were as follows. So if we simply try to count the number of times recommend appears, number of time avoid or caution appears, and make a decision accordingly, it was not working as good. So that's the second row. And when we try to introduce some sort of weights to each of these paths, how does that work? So that is the normalized weights, inverse frequency, logistic regression weights, and self-attention weights. Here also, we did not get satisfactory results. So for each knowledge paths, we used a neural network to create embeddings and used a self-attention model. That's a neural network-based approach. It did well, but the precision is too perfect and the recall is not. This is probably because the neural networks work based on likelihood estimation, whereas Bayesian works on probabilistic estimation. And also Bayesian would not require the large-scale data that is generally required by the neural network models. Intuitively, when we factor in the proportional weight of the ingredients in the recipe, the accuracy should be going up, but that was not happening because there was an issue in the text extraction process for some of them. So when we looked into how the ingredients were extracted, so the 2.5 a cup sometimes appears as 23 cup. There were enough noise in the data set to bring the accuracy down a little bit, but once that is dealt with, we should obviously see an increase in the relative weight of the ingredients. Now, obviously, everyone will have a question. So why are you doing all of this? Large language model has access to all of this information. Did you ask the large language model like ChatGPT or any other thing? Can it answer whatever that we were trying to do? So we did do that as well. We evaluated with 9 large language models of size small, medium, and big. And we evaluated with 3 prompts, one with no diabetes knowledge, limited diabetes knowledge, and detailed diabetes knowledge, exactly like as it is present in Mayo Clinic. But the model performances were unpredictable is the word that I would like to use. We were not able to form any patterns as, okay, this model can work with this prompt, that model can work with prompt 3, and etc. So these were the findings. In most cases, the models were more inclined to say that the recipe is not suitable to play safe. And these models are trained with so much amount of information from the internet. So meaning their embedding space is really large. Trying to identify where this diabetes relevant information is present is a challenging task. And as we told before, the disease specific information is also scattered. Mayo Clinic says healthy carbohydrate is suitable, but what constitutes an healthy carbohydrate is present in Harvard Medical School database. So connecting all of these information together in a large embedding space is really challenging for the large language models. And also there is a conflict between the internal and external knowledge, whatever knowledge that's given in the prompt versus the knowledge that the model has. And there is also bias towards predicting the reasons. So good fat, saturated fat, fiber-rich food item is the most reasons given by these models. Whereas high dairy fat, low fat, non-fat, these are not so much used as the reasons by the model. So given that the Bayesian approach was performing better and the LLMs were unpredictable, we use the Bayesian inferencing model to evaluate whether the users accept the evaluations in terms of, explanations in terms of clarity, relevance, and trustworthiness. So we chose 3 recipes, each recipe with 4 questions to evaluate the hypothesis. Do the users perceive the explanation as sufficiently clear to determine the relevance of the recommendation? And does the user find the explanations provided by the system to be trustworthy? And here's an example of one of the recipes that we used. And when we looked into the results for each of the question, it's mostly on the positive side, strongly agree or agree for clarity, relevancy, trustworthiness, and also the format. So for format, we can see that there is a slight inclination towards agree because we can see that the explanations are very lengthy and we are working towards a UI which provides a bit more interactive explanations. We also asked the domain experts, what do you think about these explanations? 4 domain experts answered. So for recipe 2 and recipe 3, which are considered suitable for diabetes, either 50 or more than 50% of the domain experts were lying on either 4 or 5, meaning that they mostly agree with the explanations, trustworthiness, clarity, relevance, and format. But for the first recipe, which is grilled Asian spiced pork ribs, which we marked as not suitable, that created a bit of mixed reviews. When we looked into the comments given by the domain experts, what they basically needed is they either need an alternative for the pork, because when we say something is not suitable, what would the patients do? So they want us to provide additional alternatives. And one domain expert said that it is okay for them to have all the food in moderation and it's not a problem, which actually is conflicting with other domain experts and also the guidelines given by Mayo Clinic. And this is expected in a real world scenario. But we already have a multimodal ingredient substitution knowledge graph, which is going to provide alternative explanations as well. Since I'm not evaluating the results, I did not include that in my mainstream storyline. So I also did the chi-square test to see how statistically significant the results are. Since we had 46 participants for each and every question for each recipe, we got the p-value less than 0.05, mean they are statistically significant. And to summarize, for the 4 research questions, these are the corresponding technical contributions and the corresponding papers which are published. There are different types of reasoning involved in this particular recommendation: chain of evidence-based reasoning and procedural reasoning. We do have methods to do counterfactual reasoning and analogical reasoning as well. But again, since I do not have evaluations for that, I am mentioning that with caution here. Now that brings us to the next domain, explainable AI pipeline recommendation. So why do we need AI pipelines? Sure. Why do we need explainable AI pipeline recommendation? So for the simple task of image classification, there are several possible combinations to try from to find the optimal model. It is costly to test all possible combinations. Wouldn't it be helpful for us if a recommender says that these combinations work and this was the metric that was obtained before? So this is what we are trying to do in our recommendation work, just to recap. So to start with, how are we going to extract the entities from the natural language text? For recipes, we had the recipe text to extract the ingredients and cooking methods from. What is the equivalent for that for AI pipelines? When we were thinking about these, where can we find the metadata of AI pipelines? We stumbled upon these following open sources. And it's also not possible to execute these AI pipelines to create the metadata, because we will be back to our problem. We will be back to square one with our problem, which takes time and compute resources to execute them. So these are the metadata sources that we stumbled upon. And we collected the following data through their API from each of these sources. And we also have the manuscript PDF and the images from these manuscripts downloaded so that a pipeline can also be searched based on the figures that we have at hand. When we looked into the data we extracted through API for papers with code, some of the entities were not explicitly uploaded by the user. For example, we do have a paper, we do have a code repository, but the user did not mention what is the task, dataset, model used in the paper. So generally it is expected by the users to mention that. So since view of the paper did not have that, we were trying to see, can we use some sort of extraction method to extract these entities? And here, once again, we did knowledge guided prompting of large language models to extract the corresponding entities. Given a manuscript PDF, we used the keywords to identify the subset of the sentences that talks about the dataset, task, or model, and then gave that input paragraph strict set of instructions to the large language model, and we got the corresponding output. That's generally in the text format. So we do post processing to get the corresponding JSON format out of it. The four models that we tried are as follows: Mistral, Gemma, Llama, and ChatGPT 4o. ChatGPT 4o performed really well, and also Gemma performed really close to ChatGPT 4o, though Llama is the large model in this particular table. For models, we see that the accuracy has dropped a little bit down. That's majorly because the information entered by the users themselves is of a little bad quality. For example, in the ground truth, for models, this is one example, SVM, SFT max, and I believe that is softmax. When the model predicted, these were the list of results given by the large language model, and each of these output is present in the input paragraph when I verified. So the model is doing well, but we have to probably come up with approaches in the future to deal with how to deal with poor input data quality itself. So given that we have extracted the metadata either through the large language models or from the API, we noticed two variation. One is the nomenclature. The concept model is present as methods, flow, or model. And we also saw a data structure variation, for example, between papers with code and OpenML, for example, here. So in order to unify them, we proposed common metadata ontology that has an ontology, a representation to store the metadata of end-to-end AI pipelines. It allows for dynamic inclusion of additional stages, models, and data sets that we need to evaluate it with what we already have as well. So putting them together, the information we obtained, mapping them to common metadata ontology, we have the graph integration module. And we also got the corresponding manuscript links from papers with code, Hugging Face, hit the archive API, got the PDFs and figures. Putting them together, we constructed the pipeline graph. And since it is these graphs contain a lot of natural language text, even within the nodes themselves, we also used a sentence transformer to compute the embedding, which allows for approximate search. It's a dynamic knowledge repository, meaning that it can periodically pull data from each of these sources and update itself. This is the overview. We have 1.4 million AI pipelines with 78 million triples when represented in resource description format. So how are we going to elevate the low-level data to high-level knowledge? As we mentioned before, recipe is a rich domain with a lot of domain knowledge, but in case of AI pipelines, we have to extract these domain knowledge from the text descriptions that we can find. So we did the following. First, for task, we identified the modality and category. Modality being whether it's an image-based task or a text-based task. Category being detection, segmentation that talks about the nature of the problem. And we also have the description for the tasks. Whereas on the other hand, this information cannot be obtained from the dataset names. MS COCO does not tell that it's an image-based dataset. We either need to rely on the description. So whenever the description is not present, what can we do? We did a graph-based labeling by associating which task is being performed on which dataset and identified the labels here. So for example, for the Factify dataset, which is from our own lab, it's used on two pipelines. One is based on image, the other one is based on image plus text. So the modality of the task became multimodal. We do have model classes provided by Hugging Face, which is an additional source of knowledge. And we also have task taxonomy given by papers with code themselves. So for example, here speech is a parent of speaker verification, and speaker verification is a parent of text dependent speaker verification, which is a task and also a parent of the pipeline on bottleneck features for text dependent speaker verification using X vectors. So this taxonomy also comes in handy when we want to search for speech-based pipelines, image-based pipelines, and so on. So here, let's quickly see what are the benefits of grounding even when it comes to search. After we grounded them in knowledge, when we searched for pipelines, list all the pipelines with dataset and model for image detection tasks, we got 2D object detection and 3D object detection in response, though it does not have the explicit name image in it. So the grounding was really helpful when we were doing search as well and not just for recommendation. So this is the equivalent of dynamic multimodal process knowledge graph representation for AI pipelines, and grounding them with knowledge. Each of the entities grounded with knowledge can be given to a model for whatever reasons, can be for recommendation, search, or projecting them to a latent space for similar pipelines put together, and etc. We do have figures, textual information, vectors, and also the manuscript PDFs to extract more information out of it. Now on to the research question 3, explainable recommendation. So first, in this case, we do have the task, dataset, and model, which are the major key players in a pipeline. So we designed a neurosymbolic ranking function for each of these. So the similarity of task looks as follows. Similarity of dataset and model correspondingly looks as follows, which can be either used in combination or separately to identify the relevancy of each of these components, which will help us form the overall relevancy as well. So this is the neural component, and the symbolic component here is we try to compute again the set similarity of semantic properties such as recipes. While neural component helps us gather or identify synonyms such as conversation versus dialogue, the semantic properties such as category and modality can elevate the ranking function when we say that these two tasks are text-based tasks, image-based tasks, detection-based tasks, localization-based tasks, and so on. Since there was no ground truth available for this domain, since there was no ground truth available for this domain, we had to rely on human expertise to give the evaluation. So we identified the following areas. So given a task, we identified a relevant task and its associated pipeline and asked the users or the domain experts to evaluate how relevant these results are. So the MLSKG is ML schema-based ontology. There's also an ontology for models, machine learning models introduced by ML schema themselves. Since they were not rich in semantic properties, we can obviously see that the AI metadata knowledge graph performed really well overall. And that's part of the published work. And okay, now we saw if the entities are given separately, task, model, and data set, that is how we are going to rank. So what happens if the information is the input is in the form of a natural language query? How can we deal with that? So here, the graph-based models give preference to graph topology and text-based models give preference to text. So in our case, pretty much the topology of most of the graphs looks very similar. So we need a method that will bring together both the graph topology and elevate the text information. So we came up with a knowledge-enabled graph text fusion model. So given a graph, we generate the embeddings for each of the nodes and extract the knowledge identify the knowledge of that pipeline, use a sentence transformer also to generate the knowledge vector. And we came up with this graph text fusion model. And correspondingly, now we need to evaluate this against something, the input natural language queries. So we generated these natural language queries using the information available for each of the entities in a pipeline. This is the task, dataset, model, and these are its descriptions. Give me a one-line query for each of these pipelines. So that's how we generated 2 queries per pipeline, so that given a query, we can try to retrieve the relevant pipeline out of the embedding space. So we used a sentence transformer to generate a query, create an embedding, and then trained based on the retrieval knowledge. So the graph text fusion model, the algorithm for that looks as follows. Looks as above. So we used an aggregation function to bring together the graph embeddings and also the knowledge embedding together. When we looked at the results, again, obviously the knowledge-enabled graph text fusion model performed really well. As we were explaining before, just text or just graph-based models were not working, which is GAT and GCN, graph convolutional neural networks and graph attention networks. We also use the sentence transformer or fine-tuning the embeddings out of the sentence transformer, still not the results that we would like to acquire. So when we came up with the model that brings in the abilities of both of them together, the accuracy improved significantly. And we are not seeing a lot of improvement or a very significant improvement between the knowledge-enabled model and the other model, because as we mentioned before, the availability of the domain knowledge in this particular domain is slightly limited, but still it shows that these domain knowledge plays a vital role in improving the accuracy.
Was it any
when you feel compared to the size of the model?
Yeah, I think this will explain that one. So just the slide. So again, the question in this domain would be, did we compare it with ChatGPT? Did we ask the ChatGPT, which is a very big model trained on large amount of information? So when we asked the ChatGPT to give me a pipeline for supervised anomaly detection, it gave 3 papers very nicely attached to archive links and then GitHub. But only when we looked into the GitHub links, they are not found. All 3 papers, the archive link is the same. The archive link does not talk about the papers which are mentioned here, and the data sets mentioned in the paper 2 and paper 3 are not the data sets that were used in the paper. So meaning that it produced very nice results, but none of them exist. When we asked the same question to AI metadata knowledge graph based recommender, it produced the relevant results, attributing it to the archive links for the documents and GitHub links for the pipelines, which can be used to reproduce the pipelines as needed. And that brings us to the 4th question. Do the users accept the evaluation that we are giving? And we did a very similar, we conducted a very similar evaluation similar to the recipe domain to evaluate these 2 hypotheses on 4 metrics, clarity and relevance. And we can see that the graph is mostly on the right-hand side, meaning that most of the users found the explanations to be clear, relevant, trustworthy, and the format is also satisfactory. And when we did a chi-square test for this one, we had 37 participants, which was a good amount of participants to conduct this test as well. The p-value was less than 0.05 for all the questions under each repositories. All the questions under each repository is proving that the results that we got were statistically significant. To summarize, these were the technical contributions to each of the 4 questions, and these are the published papers. Currently, we are doing only one form of reasoning here, analogical reasoning, which is explaining why the recommended task or pipeline is relevant to what the user has asked for. So drawing the similarities between the input and the output. To conclude, from both the domains, these were the 4 research questions we addressed. But if you look at it, these were basically step 1, step 2, step 3 to do the process recommendation. When we put them together, we can observe that the first half of it, which involves entity extraction, was heavily reliant on the neural network-based approaches. And the second half, which deals with decision-making and reasoning, was mainly or heavily dependent on symbolic reasoning. And putting them together, the neural component and the symbolic component, we came up with a representation called dynamic multimodal process knowledge graph, which moves beyond or pushes beyond the embedding-based representation and also has semantic knowledge for each of the entities that we have extracted. So that Euro-symbolic queries, as we showed before, given an image and asking to make modifications for an image or recipe with that particular image can be easily found. So these are the domain-based contributions. The cooking action extraction is a domain-based contribution to recipes which were not found, which is generally a least explored domain. The disease-specific knowledge graph we created for diabetes. The neurosymbolic recommendation, which uses a knowledge graph-based reasoning. And then coming up with approaches to perform different kind of reasoning to produce explainable and traceable recommendation. The domain contribution of AI pipelines are as follows. First of a kind ontology to represent the metadata of end-to-end pipelines, which can also be dynamically modified to include more pipelines without altering the original schema. And then large-scale AI pipeline metadata knowledge graph, which has 1.4 million pipelines with 10K tasks, 53K data sets, and 280K models, which can be searched or can be asked for recommendation as well. And here also providing 2 methods of explainable recommendation and also the knowledge guided prompting to extract entities out of the manuscript PDFs. And these were the relevant publications. Some of them are directly tied to the technical contribution. Some of them are works in the respective domain, which are not directly associated with my dissertation as well. And these are my open source contributions. The AI pipeline metadata knowledge graph, along with its recommender, is open sourced by HPE. And the disease-specific food knowledge graph will be open sourced working on the GitHub page. The multimodal ingredient substitution knowledge graph, which is part of a collaborative work. It was one of my intern's master's thesis, and he's the main contributor there. And the dataset has already been used for an hackathon conducted by UC Irvine and Stanford. We have diabetes-specific recipes, the benchmark dataset to promote further research, and also the cooking action dataset along with its model. We also curated recipe images to extend the dataset of recipe 1M. And I also contributed to the open source development of dynamic process ontology, which will facilitate the dynamic multimodal process knowledge graph representation for smart manufacturing as well. So now that's the third domain that involves processes, and we can apply the dynamic multimodal process knowledge graph representation there as well. So these are the list of references used in the presentation. And I have 3 patents, 1 granted and 2 of them under review. I had the opportunity to co-organize and co-present tutorials and workshops. And I also had the opportunity to be present on 2 AI panels, one which I shared with Kaushik. And these are the 3 news articles related to my research articles or blog posts related to my research. And that brings to the acknowledgements. So first, I would like to take a moment to thank my advisor, Dr. Amit Sheth. He planted the idea of PhD in my head when I was in denial. And I picked a project that was non-funded, and he gave me the liberty to pursue that or choose the topic that I'm really passionate about. And not once he asked me to switch different projects, but on the other hand, he connected me with several different people to to expand my perspective and gather as much resources as I can. Next, I would like to thank the committee members, Dr. Biplav Srivastava and Dr. Vignesh Narayanan. I have had the opportunity to work with them on several papers, and through their interactions, I learned a lot. And I would also like to thank them for being available to me multiple times to iteratively improve my presentation. It has the structure it has because of their feedbacks and improvements throughout this process. And I would also like to thank Suparna Bhattacharya. She's a very busy person, being a vice presidential fellow. But she always took time to attend the meetings about the AI pipeline metadata knowledge graph work. And she used to ask those deep, thoughtful questions that helped me highlight the novelty and challenges in building the AI pipeline metadata knowledge graph. And my final committee member, Dr. Swathi Padi, she is both my professional and personal mentor as well. She was the one who pushed me to hit the ground and stop doing the literature survey and start building the models and start making the implementation. She used to sit with me late at night around 10, 11, and she had a 3-month-old baby. And I would like to acknowledge Tara as well. She used to sometimes sit with us and make noises, keeping us entertained. So thank you very much, Swati. I would like to also acknowledge the co-authors that I have here at AIFC. I learned a lot through their interactions, and I gained so much inspiration from the methods that they introduced me to implement it in my work. And also HPE team members. Special mention to Alap, who I worked with very closely at HPE. He used to sit with me for 2 to 3 hours after the office hours to get the AI pipeline metadata knowledge graph up and running. Thank you, Alap. It would not have been possible without you. And special mention to Martin and Sergey, Tarun, Arpit, Ashish, and Jnanaranjan as well, who took their time to give iterative feedbacks for the AI pipeline metadata knowledge graph to bring it to the stage where it is. And obviously the NSF grants, without which I would not have survived as a graduate student.
Thank Sergey for attending this.
Yes, I think several of them are online. Yeah. And yeah, whoever joined from HP, thank you very much for taking your time to come and attend. I know it would be really early for Sergey. It was 7:30. Thank you, Sergey. And also whoever else joined, sorry, I'm not able to see the names here. And special mention to my interns. I know there are a lot of them, but the food recommendation work reached the point where it is. It's because of them. Throughout the years since 2020, I've been collaborating with each of them at different points in time, and all of them gave their fullest and contributed to this project. So thank you very much. And I think some of you have joined online. So thank you for coming here and supporting me as well. Next, thanks to the AISC members, I have found several good friends here as well and formed several personal connections. And we have a recent precious addition to our team who just Situmi, who just exists, smiles, and melting all our stress away. So thank you, Ruwan and Tiffany, for bringing her into our lives. Not able to find Ruwan. Oh, there he is. Thank you so much. And I would like to also take a moment to acknowledge my personal circle. Thanks to the family I found far away from home. Special mention to my girls who were my strongest support system throughout this PhD journey. And next, I would like to thank my family who dodged all the bullets about why am I still a student and not married. And and they gave me the time and they were really patient in letting me complete the PhD the way I want it to be done. So thank you so much. And my final thanks to my favorite person who's here. Uh, I have my boyfriend, Harshavardhan, who I have known for more than half of my life. And you have always encouraged me to punch above my weight, be ambitious. And here I am defending my PhD. And throughout these years, you were my constant well-wisher and an honest critic. And thank you for that. And thank you very much for the slides as well. They look the way it is because of his help. And finally, thanks to the audience who have joined online and also in presence, in person. I have, I did not actually expect the crowd that I have here. So I'm really, really thankful. And I think
Combining online and here, we are between 1775.
wow. Wow. Thank you everyone. And I know there are meetings and so many other things in your life going on, and several of you have their qualifiers tomorrow. So thank you everyone so much for taking your time to come and attend my dissertation. And that concludes my final presentation. I'm open to questions now. Yes. Yes.
Question. Very nice presentation. Very nice presentation, really excellent. Would you like to, could you comment a little bit more about the reasoning part? You mentioned, you showed some Bayesian reasoning going on, the application of Bayes' theorem. You mentioned chaining, okay, through using the process model and the knowledge graphs, I imagine. Do you support intercausal reasoning at all? Do you find it necessary to do, or issues like synergistic and antagonistic effects from different causes on an effect?
Thank you actually for asking that question, because in both of these domains, there is a very deep causal relationship. It's the ingredients interacting with entities that gives an output that alters the nutrition content and etc. I definitely see that there is a rich stream of future work that is possible in both the domains, specifically in the causal area. Right now, the only causal graph that I use is the interaction between ingredients and the cooking methods leading to the carcinogens, and probably to some extent the smoking point as well, because when the smoking point is heated, when the fats and oils are heated beyond their smoking point, they do form free radicals. So those are the extent of causal knowledge that I have, because most of them can also be marked as correlation. So right now, that's the extent of causal relationship that I have in the domain. Yes.
Thank you.
Other questions? Yes.
Firstly, thank you for the presentation. Great slides. And my question is, you showed the base model and KI Cookgen model, right? And you talked about how knowledge is playing a role, whether it's increasing the accuracy, maintaining it, or decreasing it, but making the right choice of the recipe. So the first question is, are the two architectures for the base model and the KI Cookgen the same? And the only variable is knowledge?
You're bringing two models together. So let me make sure I understand your question right. So the cookgen model extracts just the cooking actions out of the instruction. Whereas the KA cook model, the knowledge infused model, is the one which brings the embeddings closer in the latent space and then tries to retrieve the corresponding text embedding. So that model, for that one, the base model and the knowledge model, so the knowledge infused model, the architecture is the same.
I used the wrong name. I guess it's KA. So the architecture is same and the only variable is knowledge.
Yes. Yeah. Thank you.
Especially if you're watching so many audiences, except from the fact that you're a researcher.
Thank you. That means a lot. Thank you. Just collaborating with multiple people and sending a lot of personal invites. I think that's the reason. Thank you. Any other questions? Yes.
Let's say the knowledge changes, how easy it is to update your model? Because
So since there are several models involved, the ones that towards the end where we are doing decision-making process, so there it is very easy to update the model. So we just run quick inferences on the knowledge which has been changed. But for the models in the first half of the pipeline, which is heavily neural network based, so that would require retraining. But although I would like to mention that most of the models that we have used are of small size, which can train within few hours and not the big ones. So the main idea behind this pipeline is to use multiple small models that will perform specific tasks so that it's easier to retrain modularly, rather than going for an end-to-end model like the large language models where we can do Q&A based search. That would require retraining the entire model. So that's one of the reasons we moved away from that, to introduce modularity as and when the knowledge changes or even the data changes.
can I ask a follow-up? Okay. So are you saying that this was a diabetes specific or a disease specific recommender system? So can it include, or you'll have to design a separate system for a separate disease?
Got it. So there, since we figured out the first pipeline or the path, we might need to put in some efforts to gather the knowledge, but for the model changes, we don't have to worry about it. So the Bayesian inferencing that we have, we can automatically pick up the additional knowledge that we have incorporated and try to include them in the decision-making process. Only thing that it needs to make sure is the user has asked for both diabetes and also hypertension. That would be the only difference. Thank you for asking that question. That actually highlights some of the parts of my research. Thank you.
I have
So you mentioned that there have been conflicting information or knowledge available on the knowledge graphs or the ground truths that you have used. So, for example, even one of your domain experts experts kind of had a disagreement. And when you want to ground the truth, ground your explanations or your recommendations on the basis of knowledge, and you find conflicting information sources, say Mayo Clinic gives a recommendation and USLTC gives a different recommendation, how do you choose which one you want to go for? Along with that, if you have a new updated knowledge that is conflicting or in some way not as per your current recommendation, how would you tackle that issue?
Thank you. So to answer the first question, there are three ways to go about. One, if we are deploying this model to a specific hospital, let's say, then we will just go by what that particular domain expert says. And there will obviously be some conflicting information among the domain experts that's going to be universal and in all the domain. So we will do what we just did. Instead of 4 domain experts, we will identify at least 10 or 15 of them, find the sentiment that's mostly accepted by most of the domain experts, and you can opt for that if you are making the model public. And for the last one, whenever there is a conflicting information, again, the 2 things that we can potentially do is see what is the most recent publication or research on that area and see what that result is saying, if there is a conflict, or just asking the domain expert would be the best possible way at this point. Because since this is a healthcare domain, we just want to be backed by some licensed medical professional.
So if I understand correctly, because this is a crucial domain or a critical domain like healthcare, you would not want to automate the process of giving the recommendation, but that is where you would want to make a human decision as to which recommendation or which information we should go on.
Yes, it's very much so. Because the interesting thing to note here is when I presented the results of large language models, most of the large language models inclined to say that the recipe is not suitable. They are trying to play safe.
Yes.
But the domain experts were saying completely opposite. Don't tell the patients that this is not suitable. Either give an alternative and everything is fine in moderation. So these two were itself is completely conflicting, right? But on the other ends of the pole. So that's probably one of the reasons for such domains, we should have domain experts in the loop, iteratively improving our recommendation model. And going just based on what is in the internet can result in the results of whatever we got for all of those LLMs, including ChatGPT 3.5. Yes, Dr.
Yes, following up on this question, if I may, how closely did you work with domain experts? You know, I haven't unfortunately read much of your work. I haven't checked your co-authors list. How hard was it to learn their language, to understand the domain carefully?
Got it. So for one of our projects, we worked for about 2 years with the domain expert specializing in diabetes. In that work, what we were trying to do was we were trying to build an app. When taken a picture of the food, we were trying to get the carbohydrate estimate out of it. The picture-based estimation proved to be really challenging because of the old CV techniques. But through some of the inputs given by the user, 1 cup of rice, 3 cup of something, we were able to estimate the carbohydrate, and the patients found the app to be really helpful. So when we were building this app, I think for about 2 to 2.5 years, I was constantly in touch with the domain expert, learning a lot throughout that process, which led to building the diabetes-specific disease knowledge graph that we saw here.
Did you work with Ashoka, with our public health? So mention that.
That's true. So I also had domain expert collaborators from India, from Ashoka University, and also from our public health department, Bree Turner. A little bit of interactions with them as well. So those were really helpful. And the first work that I mentioned, she was a practicing clinician at Prisma Health.
Thank you.
UCI.
Oh, so we actually, thank you, Dr. Shed. So we also are in touch with UC Irvine. So there are efforts led and guided by Dr. Ramesh Jain and his team as well. So we were in touch with them for several years actually to gain a lot of insights. And we also worked with a large-scale nutrition database company named Edamem. They have about 2 million recipes in their database. So we gathered a lot of knowledge from, that knowledge, not this knowledge. So knowledge from knowledge through the interactions with them as well. How did they label their food as diabetes friendly or low carb diet, high fiber diet, and so on. So they did have a list of diet labels and disease labels. So through the interactions we had with them, we were able to gain good bit of knowledge to implement the work that we have.
Thank you.
Anyone quickly wants to ask question online? HP colleagues or the interns?
Okay, I can go. I mean, I can say this. Sorry, yeah, this is Suparna here. Yeah, wonderful presentation, Revathy. And So I think I probably would have never thought so much about food and all of the elements that are, going into, healthy food. So that's a very interesting angle. But I had a question about the AI pipeline knowledge graph recommendation, since, you worked on your thesis at a time when the field, you were saying that the things are changing rapidly, and you kind of worked at the time when the field actually exploded with generative AI and everything.
Right.
So looking at that, is there something that you would have probably wanted to do a little bit differently, or do you see a direction for future work that you think would be particularly interesting?
So thank you, Suparna, for the question. When things exploded, it had its both pros and cons. So the con being so many models being uploaded to Hugging Face. And when we try to fetch those models, it actually takes quite a bit of time to hit the API and get the responses. The script runs for about a couple of weeks or more. So it seems like a little difficult to keep the AI pipeline metadata knowledge graph always updated. But the pro being, given that there was an explosion in the LLM-based model developments, it also helped us experiment with different models to extract the entities and knowledge out of the descriptions that we have. Given the scale, it is 1.6 million pipelines we have. It is not possible to manually gather the knowledge for each of these pipelines, and we have about 8 million nodes, which on an average like 8 to 9 nodes, 8 to 9 entities per pipeline. So the LLMs actually helped a lot. All these text-based models helped a lot in extracting relevant knowledge out of the descriptions we had. So that is the pro. That is the pro to the work. Did I answer the question, Suparna?
Yeah, thank you. Yeah, thank you. Yeah, thank you.
Thank you.
So the committee will get an opportunity to talk to this. So I will just ask one general question, which I didn't see anyone ask. So I'll ask that, and then we can end the session. My question is, everything in your title is fine except the word dynamic. So the dynamic about everything you did, and how dynamic is it?
Okay. So the dynamic aspect is for the following. In the case of recipe domain, let's say we want to make a modification to the recipe by replacing the cooking method or the ingredient. What ingredient or the cooking method? We have, let me actually go to the structured representation we have. So the structured representation that we showed, which has the ingredients and cooking methods separately. But it's okay. I think I'll just say it verbally. The ingredients and cooking methods are explicitly separated. So when we want to replace a particular ingredient in the recipe, it's very easy to identify the nodes where it is present, remove them, and add the additional node, looking at the compatibility with the cooking method. So that is the dynamic aspect of it, meaning that the ingredients and cooking methods can be modified, altered to make new recipes. So that's the dynamic component there. In case of AI pipelines, let's say that I am training a pipeline for entity extraction from semi-structured EHR documents. I tried it, let's say, with BERT model and a particular data set. Now I want to train it with a different model and pick a different data set. So when we did the first execution, we would have generated a metadata knowledge graph for that AI pipeline. So it's very easy again to go and add the additional executions, additional stages to the current existing AI pipeline metadata to make the modifications, and also to compare the results in a more effective way. So when we have all the models and data sets under one roof, it's easy to look at the best execution path and see which among these combinations of data set, pre-processing techniques, models work the best being either a better explanation or the results, whichever one the user would prefer. So this is the dynamic part.
We'll talk more, but probably you're looking for extensible, not dynamic. Dynamic has a notion of time, whereas versus static. We'll talk more.
Okay.
So thank you.
Thank you, everyone. And for the people online, I think except the committee members, the rest of you all have to drop. Thank you so much for taking your time to join my presentation. I'll talk to each of you separately later. Thank you.